and a small one. So the one will drive quickly to the manifold, and then the solution will follow the manifold. So you can restrict yourself dynamically. Instead of working in the system, work on the manifold. So you reduce the dimension and basically embedded the mosquito inside the human equation. Basically, that's the idea. And this was extended to infinite dimensional systems, so it's not just for ODE. For the ODE, it's very simple to do the time scales. When you go to infinite dimension, you put space on it. You have to deal with metrics, with the distance. It's a little bit harder. It depends on the equation. This one is from a group in France, Pierre Magal, that we do in just this space operator here. It's an infinite dimension space. So what you want to do is actually try to use this in the state of São Paulo. So we want to model it, which is the infinite dimensional dynamics that we are going to put in it, and try to approach this one. These are real data from the state of São Paulo from several years, so it's the incidence of a dengue, and there is this more or less mapped, divided in municipalities. So you see there's always a hope to well, São Paulo it's apart because it's so huge that you have a dynamics inside the city, so look a little bit outside. And actually, it never starts in São Paulo, it starts in smaller cities. I think there is one that's a fixed point here to start, is Rio Preto. Don't ask me why, but if you see the time series, Rio Preto is always someone that started. So that's the challenge. Once you have one city that you have an outbreak, which one is the next one? And they are not, you see that's, it's not a local problem because you're not spreading like a diffusion. You have one burst, then another city that's, well, it's really far here from one from another. It's not 10 to 20 kilometers, it's really far. So what's the next one? The basic hypothesis here is that this, and the mosquitoes are more or less local dynamics. They don't fly this distance in one day. So what is spreading is actually also the humans that are spreading. That's a basic hypothesis that we use. So what we did, for the infinite dimension, the continuous case, that's my math part, we wish to use a non-local operator like this. That's a Neumann operator. J is a nice kernel. In the application that I'll show you, we'll disappear and put a transition matrix because we discretize the system. But for my math part, that's an interesting question. If it works the singular perturbation, it does. So that's the toy model. We are working with a higher degree, but that's for the mosquitoes, we'll put a Laplacian because it grows like a diffusion. It's very slow. And for the humans, it's the no local spread. And you put a small parameter. What singular perturbation, if it works, says, just put epsilon equals 0. So we related the infected humans with the infected mosquitoes and plug in the equation. That's the way to lower the dimension. So that's what we did. That's the math part, so bear with me here. So that's the no local equation. You just do asymptotics. You can prove to put epsilon equals 0 and just plug in the equation. That's the manifold. That's easy here because you can just invert. It's very easy. And you have a nice equation in the limit one. And that's the incidence, nonlinear incidence now. And actually, this kind of equation, without the infinite dimension, just the OD, was studied as a nonlinear incidence rate, for instance, by Huang and stuff like that. Has nice bifurcations, like Bogdanov-Takens, this kind of, just the OD here. So it has a nice intricate dynamics, just the OD part with this nonlinear incidence rate. And they used to model other kinds of contact units. But that's the way we try to plug in here. So the first ingredient is try to get rid of the mosquitoes. You plug in this in the OD part, just start with the starting city, for instance, this one. So in the beginning, that's just what we want. We just want in the beginning of the illness, just once you get an outbreak. So it's really in the beginning of the time series. So the hypothesis is that that city is more or less isolated. The unit is starting there. So just fix the OD for this start and try to get the parameters for that city. So that's the OD that we put in one city. Those are more or less the parameters. And the small parameters appears between when you get both the mortality rate for the humans and for the mosquitoes. That are really different time scales. And that's where we put the small epsilon. So what we get, that's the limit equation. That's the one that we have. So we put in the susceptible and infected mosquito. That's basically where we plug in the mosquitoes here and here. So that's just humans. So that's basically the model that we want to use in one city. And this we can, if we are isolated, that's for San Jose do Rio Preto, for instance, in 2008, you can really try to fit the parameters for that nonlinear equation just in the beginning. Okay, so you can get the basic parameters from that starting point. So that's the first ingredient. Just for one city, just an OD, you can get the parameters from that. Now I have to plug in the other cities. And that's where the other problem appears. How one models the human mobility inside the state of São Paulo. That's different, for instance, from the flu that gets in Asia, that you can count the plane and the number of people that are in same plane or ships, so you can count on it. In this scale, it's kind of hard to counting people moving around 100 kilometers, 200 kilometers. So we need to get other kind of data. And we got this one. It's not perfect. It's not what we wish, but that's what we get. We get in touch with a local, actually that's a unicorn, a startup that works with apps for mobiles. So every mobile phone, when you ask for an iFood, for instance, it goes to an app that gives the location and stuff like that. That's one company that do this service of location. So he has, well, terabytes of data. Each one that gets a phone, a game, or something that needs a spatial location, it goes to that firm and then pinpoint your exact location when you say, yes, you can track me to send me the food. So in this company. So, well, actually for their business work, they need to assure that they are not spreading this information around. So what they gave us was anonymized data for movement. So just we are starting to work with it, so it's 30, well, it's an year of data, and that's the number of events that they send us for just for this year. What is an event? They can send us the data for movements. So when we get an event, what it is? It's one starting point, and that the next time that he used the application was in a different location. So it tracks movement. So you ask iFood here, and then you go to another city and ask iFood again. So in this time period, you are tracked by the company in 2 different cities. So they gave us this vectors. It's like so each event is like 3 locations. The first time you use the application, the second time you use the application, the third time you use the application. So you can track, and it's the same individual in each event. So we track movement. So it's not perfect, but you can do some statistics. It's more or less spread evenly through the weekdays. If you plot the time series, we are very predictable. So if you look, the movements is almost the same every week. Well, it differs a little bit if it's a holiday, it's not a holiday, it's Sunday, but it's more or less constant. And what we did from this, the first thing we put, and we did some transition matrix. So we tried to put what's the probability from being in one city, for instance, choose São José do Rio Preto, and say what's the probability to be in another city in the next time. And that's what is more or less graded here. It's very small because most of us is staying around the city, but you have some positive probability to go to cities that are really not close. And you can choose the time frame that you want to use, if it's after 1 hour, 2 hours, or the next day. More or less 1 day will be enough for us to do that. So we did that, and we did that for any day of the week. It can be heterogeneous in the time frame, or you can just take average and see it's one transition matrix, and that's it. That's the first approach we did that. So just take average. There are a lot of uncertainties. That's one. So that's for Sunday, for instance, and this is for Wednesday. Or there is a fixed point here that you always go with a positive probability to Ribeirão Preto, for instance. I don't know if Botucatu is not even here, but so it's not going for Botucatu. So it's, it's here, but it's not. There are nice places, for instance, the Santos, that's a big port. There is some kind of movement that's positive also from São Paulo, so it stays in the beach a little bit and then goes to São Paulo, so you can take this kind of movement. So that's the point where we are in this part of the to predicting. So we can adjust the parameters for the city, and we have the transition matrix. The open question now, will be enough to get the forecast of this probability. So we are estimating the R0s for the next city. With the transition matrix, we got the R0s for the network. So now we have the network, you have the R0 for the first city, and then you plug in the transition matrix. We still have the challenge because we do not know the complete parameters for the other cities because we embedded the mosquitoes in the equation. And the mosquitoes are really different. So that's the part that we are as a challenge as how we proceed from that. Doing simulation, we did a lot, but still that's not enough for us to take the whole, to answer the whole question. Which will be the next city to get the illness? Well, how can we set up a risk map, really a risk map from the first event? Okay, so that's the first approach. The second approach we did with a different state. Sorry about that, it was different time scales. So the first one we did one period, and then the next one we did another period. So this one we did for the state of Rio de Janeiro. And was based in this little nice work by the group in Bahia. They construct what they call a spatial temporal correlation network, simply observing the time scales, the time series. So they put the time series and did correlation between the time series to try to get the spatial network. It worked a little bit, but was not that good, and was not enough to get, sorry about when it blew up. That's the incidence for the state of Rio. It didn't work doing directly correlation for the state of Rio for each year. So we had to think of a way to follow this idea, but have to change a little bit. We cannot do direct correlation between all time series. So the idea was the following. So if we get a time series from what we call the focus, for instance, starting this city in this year, and then spread to the whole state. And we have the time series for all these municipalities. So if you start with one city, it's not that clear that we are going to do directly correlation between the two time series. What will be nice is, well, you have the first city that starts, and then you have the second one and the third one. So you have a time shift from starting one city, and you have a delay for this illness to spread to the other city. So what we did for is exactly like that. We got the focus, the starting cities, and then we did correlations shifting a week, 2 weeks, 3 weeks, and then we try to construct the correlation network. And that's what we did. And that's for the year, I think it's 2008. This one, sorry, I didn't write it. So we got the focus. That's the 3 cities. That's more or less the week that got get the threshold. So there are 3 cities. It doesn't matter the names. Actually, Cantagalo is very close to the city of Rio, Natividad also, and Angra is kind of far from Rio de Janeiro. And, well, that's the number of people. And then from that, we did correlation with other time series, but shifted from 1 week and then from 2 weeks. When we get positive, not all the cities are correlated, but some of them are. And that actually this one were correlated to these cities, and the other one, that's Angra, was correlated to Paraty, and Natividad was not correlated with any one of those. So what our assumption? That this is the network. It starts in Cantagalo, and then it spreads to these other cities. Okay, so that's very easy to do it. So you get, well, you have to normalize, that's some statistics to do it, but once you find the focus, you can shift the other time series and do correlation to see if a network works. Actually, that's far from getting something that works. That's very nice once the unit has passed, isn't it? Because I can do time series. But one question is, if we have all these correlation networks, do we have a pattern? That's basically what we want to extract from that. And how do we check that this is working? That's another question. We got some time thinking about it. And then it came Roberto and showed us a little bit of what I said about the nice theorem that can reconstruct the attractors, and they apply to do causality. And we try to work a little bit. That's just tests. We use a package, so we're not that courageous as Renato did all the programming in Python and everything. We use this little package that they try to use this convergence cross mapping that allows explaining that you can take one variable and try to reconstruct the whole manifold. Here is a little bit more difficult than just looking at the Lorentz attractor, because the Lorentz attractor, you know the dimension beforehand. Here you do not know the dimension. I don't know if they have 1 city, 2 cities in the network, 3 cities, 4 cities, or the whole state is connected. So what we can do, we can test. That's what we did. That's the Sugihara original paper. That, thanks to Roberto, we get in touch with that. And that's the time series. That's one group of time series with Cantagalo. That's Paraty and Angra. And then we mix a little bit, Cantagalo with Angra. When put Rio de Janeiro, then the number of cases goes to hell, but they are all here grouped together, and they are more or less the same. You know that, for instance, Cantagalo and Angra are not correlated because you have like these 2 different peaks in one, and the other one is nice and smooth and go ups and down. but so they are not positively correlated. But they are more or less all the same if you look at the time series. And we did a test with the correlation. And as Lai said, one thing that's very difficult is to know the embedding dimension. So we have to check for several embedding dimensions. The embedding dimension is the number of steps that you go on the time shift in the time series. So how you reconstruct, as Lai said, you take the time series and produce up, that's one dimension, it's just one dimension variable, it's one observation, and we embed it in the whole dimension of the system that we have no idea what's the size of this dimension. So what do? You take one observation and produce several dimensions just shifting the time series backwards, isn't it? That's what Lai explained. So I can put in any dimension you want if I have a very big time series. So that's the number here. And that's the correlation rule that you can, the forecast skew that this package says. And of course, if I do a huge dimension, I get the whole state, so everything is correlated and is worth it. The nice thing when you get lower values for the correlations, okay, it's like between 5 and 6, because I have two cities, you have humans, mosquitoes, so it's more or less infected, susceptible, so you expect to be between 5 and 6. I think it's something.
But what is this forecast skew?
That's the whole from the correlation, because they use this. Sorry, I was too fast, because I thought our talk was so good that what is this conversion cross mapping? What they do, I should explain that a little bit, isn't it? Because well, let me draw a little bit. So you have for instance, the Lorentz attractor here, and you take one time series here, isn't it? And then with that, doing time lags, you produce another manifold. That's the shadow manifold for this one. So what it does, since you have this embedding, I can try to see if this embedding is nice. So I have another observation from this time series. That's the other one, isn't it? So for me, those are the two time series for two different cities. But the system is the same. So I can use this time series to reconstruct my manifold again. That's the idea that Roberto uses also. I'm just copying things here. So from this time series, I produce another shadow manifold here, isn't it? That should be close to the original one, and this should be close to the original one. So what this little package does is something like this. Well, do I have to? If you have one time here, so this time is related to this one, is it? So if I go here, this time is in this manifold. So take the three closest one here, isn't it? So you will be three different times here that will be related to these 3 points here. And take these times and look for the 3 points in here. So they are correlated, or you have causality, if this thing are close as this thing are. That's more or less like this. Roberto can explain better than me this thing. So you have correlating how close are this one related to how close are this one. And that's the whole, basically, if I'm not cheating a little bit.
I'm going to talk about this tomorrow.
Also, he's going to explain everything, so I don't need to talk about this. So tomorrow, part 2. So those are these holes. So higher the hole, more you have more, because the correlation is in the time series. Once you have the time series, you have the distance the difference between closeness here and closeness here.
So the higher the hole, the more
Well,
correlated the two time series.
yeah, you look for the center one here, and you look for the center one here. So you have produce a new time series that should be close to this one.
The hole is then just a measure of distance between the
It's correlation measure. So we are looking for correlation. So it's a correlation measure between the time series that you create by getting 3 points together from here and the 3 points that are together here.
So the higher the best.
The higher the best, but you see everything is high here. It's almost correlations are 0.8, 0.9. But the nice thing is when you get a lower number of the dimension, that correlation is high. Well, that's one way to see that. I don't know if it's good enough or not good enough, but it captures a little bit this direction. Okay, so for instance, from Paraty, you can be predicted by angle and something like that. Okay, so that's what we are trying to do. So there are two really different ways to do it. One is pure like using the dynamics of the equation, and this one is pure correlation. I'm using the people from statistics to do that, but that's the way that we are using it. But I think that's what I have to say.
Thank you.
Okay. So in São Paulo state map, so do you have an idea of the number of decays or of the color that you are using? So is this
Yeah,
the absolute number of cases or is normalized?
That's incidence. It's the new cases there.
Okay.
And I will not remember by heart how do you color it, but we have all the time series. So
Yeah, my question is the following because
you
how
put a
much
threshold. So
Yeah, but how much can we trust the data? Because I know that Rio Preto has a very good surveillance program,
Yeah.
and the other cities don't. So how much can you trust to do your
because
modeling?
that's the number of cases. Notified number of cases first of all. So it's notified number of cases. So there is no, for instance, the asymptomatics are not here, and this is averaged by the population. So you have an average here. It's not just counting. So you count and divide by the number of population. And I know that's directly the time series that we have from the database, from Sinan database, and just divided by the, yes, that's Sinan database. So well, if you can trust Sinan, that's the data that we have. So that's true data. Yeah.
What percentage of the Sao Paulo population use that app that you have so that you can have an idea of the population movement?
We actually, that's the one of the, it's very hard to do statistic here because we don't have that many, because all this thing, let's say, first of all, this is anonymized, okay? So it's anonymized, so how did they did it? So it's not just exact point. They put, like, for instance, first of all, a huge square between 0.2 latitude to 0.2 latitude. So everything here is the same point, first of all. So that's huge. Second, they send us the number of users. For us, it's much more than that. That's millions, really millions. But I don't know if it's the same or not, because the database is changing. Once you have one, they know if it's the same person or not. But if they access from two different apps, you can miss this information, so they continue cleaning up the database. So the total number of users, it's not known in this database. So I cannot do a statistic if it's... That's what we are trying to talk with the company. How much data do we have? What we agree is that we are starting to work with. If it's promises, then we can get together. Well, I want to get this thing smaller. I want more data from to do statistics, but it's not that easy to do with private companies, and they are trying to survive also. So,
Hey, Sergio.
Yeah.
Nice presentation, thank you. My question is also on the same topic. I wonder if you had any chance to compare what comes out of this data set, especially during weekdays, and what we have from from mobility to work and study from the census data.
From the census data. Well, first of all, yeah. As I said, this data is very rough. Okay, so the census data, the ongoing and outgoing is better. For the city of São Paulo, is very nice. The metro has a blue book, or that is a very nice probability from being in one place and going to the other one. But that's not so good when you go to different cities. The census is not that good. For instance, they have in the census what they call work if they leave one city and work in the other one. Yeah, we have this, but we did not compare with this kind of data because it's, for instance, São Paulo, it's between two boxes, okay? And there are boxes that are more than one city, okay? Because this is huge. 0.2 latitude is very big. So it's hard to compare directly. Once you have from the census, you have from different cities, they can be in the same box. So, and as she asked, I don't have the total number of users. Okay, so, and we got out from here the people that start in São Paulo go to another state. That we captured that also. Okay, this is just data for starting using inside the state. So we are not capturing people from other states that the second event is in São Paulo. Okay.
More questions? Thank you again.
Thank you.
So last speaker now is Gustavo Sivona from University of Córdoba.
Córdoba. Vou tirar aqui.